Thanks, Matt. So I'm not a faculty member, but I have been a researcher for some time. And yes, that story about writing the C code, the time gets shorter every time I hear it. So it was more like a week or something, okay? So just for reference. But since you gave me the segue, what is true is that I wrote a significant fraction of it while sitting under this tree in Camperdown Park, all right? So that's the seL4 tree on that bench. Okay, what I'm actually here to talk to you about today is the folks who I've started working with as head of verification, and this is neutrality. And the idea behind what we're building there is that there are challenges for particular sorts of organizations which are not well addressed by existing solutions. In particular, there are places like NGOs such as, this is a bit of a Switzerland-focused slide, you may note, but the Red Cross, for example, who operate in war zones, they are the target of state-level threats, but do not have the internal engineering technical resources to really defend at that level. And so the idea is to provide them with a virtualization platform which can really give them isolation that they have a chance against these sorts of attackers. And the idea is that we are able to provide a sovereign and neutral solution. Very Swiss-focused pitch slides here, okay? The team at the company is quite small. This is all of us. The original version of this slide had me as a co-inventor of seL4, which I wasn't comfortable with actually claiming, but I was there early on. So the technical folks are me, Mathieu, and Stevens working every day, and there are a number of other people involved including Gernot. So the pitch, and this is very much the sort of the generic pitch slide for the company's work. People here will have much more detailed questions because we are in fact building on seL4. Please feel free to put up your hand and press me for the more detail, because this is the version that I can give to absolutely everybody. And so, but that said, the overall pitch is you should be able to get the efficiency of native execution on a cloud hypervising using full hardware virtualization, but with security equivalent to running each of your VMs on a physically separate machine. And this is the property we're targeting for this hypervisor product that we're developing. The threats we're concerned with, so the principal ones are listed on this slide, although it's not completely exhaustive. The first being VM escape, where you compromise your VMM and escape into the broader system. The second, cross-VM attacks. So if the VM has managed your memory incorrectly, you end up being able to write to somebody else's text segment. The third being compromise of storage outside of the machine. So cloud systems generally don't have the storage on the physical machine that's actually running the compute. It's somewhere else co-located. And the fourth being compromise of the management plane itself. So this is getting into the hypervisor's control interface, compromising that, and then of course, you're into the whole thing. And the promise of the Atoll platform is that by running it on your hardware, you'll be able to get a view of these separate, securely isolated machines that are actually running on the same physical platform. And so the key elements of the design that we have selected to attack these particular threats are firstly, to address the threat of cross-VM attack. And given my own personal background with a bit of work on side channels, which I did during my PhD here at UNSW, one of the lessons of that work and work which has followed up on it is that you've got this enormous amount of microarchitectural state that is shared between cores within and it gets worse and worse and worse the more closely you share this stuff, right? And so when it comes to looking at things like side channels and other things like, for example, Spectre, our design is that you do never share a core between two mutually untrusting VMs. The hardware we're running on is selected as modern ARM server hardware. We have selected specifically because it allows this to be done relatively efficiently. You have large numbers of cores, which in practice, you actually can't power all of them at the same time. You don't have the power budget. And so it's actually perfect for this sort of separation. Secondly, the VMM is in the trust domain of the VM. We assume that every virtual machine monitor is compromised from the get-go, And these are isolators. The VMM is the component that's emulating the machine, pretending to be a PC or whatever you want to run on. And we're using the term hypervisor for what sits underneath that. And of course, in our case, the hypervisor is actually a seL4, and that actually configures the stage 2 translation to isolate these things. Thirdly, to address the risks of compromise of your storage, in our model at the moment, your storage is on an iSCSI share coming from a SAN. This is all transparently encrypted, and this encryption is done within the VMM, which may sound a bit funny when you take into account what I just said, that we don't trust the VMM, right? But you've got to think about what the trust models are for each component of the system, and the VM is always trusting the VMM. It can't not trust the VMM, right? It has control of it. So any compromise of the VM would already be bad enough. Excuse me. And so this is actually an okay place to do the encryption. And thirdly, as a defense against management plane compromise, there will be a narrow, formally verified configuration and management and deployment interface that is exposed outside of a machine actually running the Atoll Hypervisor platform. So there's as small an attack surface as possible. And finally, in order to prevent cross-VM data access, as opposed to, say, side channels, or direct compromise of the management plane, all of our resource management will be done using capabilities. And usually this is the point in the talk where I have to explain what seL4 is and then it provides capabilities. Thankfully, I can mostly skip that today. But this is why we are building it on top of seL4 specifically, because it will give us this high level of assurance about resource isolation with the security of the existing proof, the existing 20-odd years of proof effort. And so I will give you a brief overview of what the Atoll architecture actually looks like, how we are building this on seL4. And again, I apologize if the slides actually, in contrast to previous talks, right, you may find that my slides are a bit too high level. And so again, please ask me, put your hand up and ask me for the details if it looks like I'm skipping something you think is important. But the Atoll hypervisor will be built on top of the seL4 kernel in the multi-kernel configuration. So the types of machines that this will be running on are things like Ampere's current range of chips, the Max and the Ultra, where you have this large number of ARM cores. Each of these ARM cores has a separate L1 and L2 cache, and the majority of the cache memory in these systems is actually in those separate caches. There's a small shared L3, which is effectively just a staging post for DRAM accesses, allowing coalescence and so on. So from a side channel perspective, this is actually very nice. Okay? You've got these large number of cores. Each one is running an instance of seL4. And again, this is where I usually explain that, okay, you've actually got formally verified secure access to all the resources in the system, and this includes not just the RAM up the top, which may be shared between multiple different VMs, but also to the ability to run on the CPU, right? The ability to actually schedule something on the CPU is something that requires authority, and this is securely managed as well. But this is something that for this audience I think is fairly self-evident to begin with. But what you can see in this diagram is that we support multi-core VMs. There's no limitation on the number of cores you can assign to a VM or the amount of RAM you can assign it. The RAM is assigned out of a large global shared pool. All of the memory that's not assigned to one of the kernel instances is available for any VM that starts up. This is all fine. And all that matters is that you've got this node manager component which sits below each of the VM instances and is effectively its trusted counterpart. And this is what's responsible for creating the VM instances, creating the threads, setting up your C nodes, and so on and so forth. So this node manager is the key part that we verify. Additionally, all of the infrastructure that's needed to support it, on top of the verified seL4 microkernel. So again, I won't bore you with the seL4 is great, rah, rah, rah. We all know that, okay? But yes, you've got years and years of proof. But the important thing about this slide for this audience is that we intend to build on top of the existing proof stack. So all the way up to now, what I've been able to actually guarantee, so as I say, the company is building this hypervisor. They took me on as head of verification earlier in this year, and I've been sort of working through and talking to the Proofcraft folks a lot to coordinate on the roadmap, to make sure that we are building on things that are actually going to exist, and hopefully we can contribute back as much as possible. What we are targeting right now is the integrity level. We will be extending the integrity proof to a multi-kernel, and then lifting this one stage up to actually talk about the VMs, right? Explicitly, that access between the VMs will have the same integrity property that you are familiar with on top of seL4. Information flow, so this would be like the confidentiality proof. That is something that we would love to target, right? It is, of course, a good deal more difficult. That is sort of on the wish list, all right? But in the first instance, what we'll be giving is the integrity result between VMs built on this machine. So the seL4 multi-kernel that we are building on, so again, these slides are dual purpose. So this is where I have to explain what a multi-kernel is, which I think probably is worth going through a little bit, even for people who are otherwise familiar with seL4. So I also have a sort of a second life as one of the Barrelfish developers for, 10 years or so. So I am obviously heavily influenced by that design. But independent of that, the multi-kernel really is the right choice for lifting a large amount of existing proof effort without extensive modification, right? So the idea, of course, being that yes, you run a completely separate instance of the kernel on every core. And the original intent behind this in the Barrelfish design was for scalability. The idea was that getting locks between cores was one of the key bottlenecks in, for example, scaling Linux to SMP systems, right? This is one of the famous problems that arose, right? And so the idea behind the multi-kernel is to say, okay, well, what happened if we went all the way to the other end and just shared absolutely nothing, right? So that the individual kernels can all complete atomically and locally without having to reference each other. And then any coordination that needs to happen between these kernels, Barrelfish calls them the CPU driver, because they're not really doing a lot more than that. Although actually that term was originally from Chuck. I don't know how many people who are here actually ever met Chuck, but I know there'd be about 3 or 4 perhaps. He came up with that term, the CPU driver, and it's now the official term in Barrelfish. But the idea is that you do any synchronization that needs to happen at one level up. You build explicit distributed systems protocols in, like a 2-phase commit, to actually make changes to the system. Now that higher level, most of what Barrelfish is doing there is worried about transferring capabilities between cores. seL4 doesn't need to do that, right? At least in the models that we're talking about. The capabilities, as you can see, I've written down the bottom there, strictly partitioned for everything except a pool of memory which can never become a kernel object, right? These are the things which are currently called device untyped, a name that I'm going to petition that we change, right? Because these really are just shared frames. But the important point about these things is that they can never become a kernel object. These things can never end up holding a capability. So they have a strictly lower trust profile than other memory in the system. And this stuff you can share, right? You have a big pool of memory, you can assign it between the cores, and you can rip it out, put it back, because it doesn't affect the correctness of the kernel, right? It never can. So, building on the multi-kernel, it was originally built for performance. It also is really great for verification. Yes, do the multi-kernel, please. And to the extent that I can, I would love to help. So, talking about verification, we will give the top level, the aim is to give a top level result that says that we have the integrity theorem holding between virtual machines at the top level, sitting on top of the seL4 microkernel. We will build on the long history of seL4. Yes, seL4 is awesome. And our intention is to contribute all non-proprietary components that we develop back to the community. So there will be a small component, which is the node manager and the other parts that really are specific to Atoll, which will likely end up being closed. But we do intend to contribute to the multi-kernel verification effort as far as funding and resources allow. So finally, I mean, what else do I have to say except to give you an advertising slide? You can have not just secure and efficient, but verified isolation if you run Atoll on top of the seL4 multi-kernel and build on 20 years of proof and engineering effort by the wonderful folks in Sydney. And with that, the last thing I need to say is that we will be hiring if people are looking for jobs. So at the very least, we were looking to hire somebody on the engineering side basically immediately. And we are open to remote work for anybody who is interested. And we are Swiss, so we're used to paying in francs. And then at some point in the next year, I will have the opportunity to hire proof engineers. And so if that is something that sounds interesting to you, come up and talk to me afterwards. And I'm happy to take any questions about the extra detail that I didn't give you. Thank you.
We have loads of time for questions.
How can we trust if it's closed?
Yeah, so that's a good question, and one that I think a lot of we're going to have to work with. We're going to have to struggle through as a community because the realities of actually being able to get money to do this stuff means that somebody's going to insist that you've got to have some commercial advantages. This is stuff that I have no control over, right? And you've actually asked a really good question there that I have to admit that I don't have a direct answer to. For anybody deploying this as a platform, I think the most reasonable model will be like a source access license, where people can get the source, they can get the proof, they can rerun the proof. So that way you can know that it's that the version you're running is secure. That is not as good a story as the kernel, where it's open and people have looked at it. And yeah, I don't have a compelling answer for you there yet. Well, exactly. I mean, this is what I was saying, right? With a source license, you can go, you can check it, right? So that's, yeah. Kai, yes?
I wasn't here to answer that, but I think you can do some fabulous zero-knowledge proof thingy there. And give that to the world, and your customers can have more, whatever.
Yeah.
But what I wanted to ask is, you had on your slide something about info flow. What are the properties you're after there?
Right, so as I said, this is more aspirational, but I've put that on the slide there to cover basically the confidentiality results specifically on seL4, right? So this is the explicit information flow. I mean, where it was like this intransitive non-interference, that was what the thing. It's like, to get it, you've got to restrict the system a lot. Right? Because, I mean, information flow very quickly gets non-interference is impossible, right? You can't, in practice, do it without really locking your system down. But there are some potential customers who say, yes, this is a thing we'd like. So mostly that's there so I can point to it and say, well, look, you know, if you really want the confidentiality result, you really want this proof of no flow through overt channels, then we could do it. But there'd be work. It's the confidentiality result, right? That's what it is.
So I'm interested in the node manager. I don't know, can you say more about that? Is it essentially the capability manager for the VMM, and the VMM calls into it?
Yes. So that is the component which actually has the capabilities, and it is responsible for creating the VM, assigning it its memory, and so on and so forth, setting up its interrupts. The VMM shouldn't actually be calling into it very much, right? There's almost no dynamic behavior here, right? These things are really, so the node managers and everything, these are statically created across the system. And then the node manager's job is to be the interface to the dynamic world. And its job is to create and tear down VMs, right? On command.
How can you have an information flow confidentiality story when all the VMs talk to the same network driver?
Basically, you can't, right? But that's okay because they don't. So this is part of the technical detail that I, was hoping somebody would ask me about. All of these VMs are directly using SR-IOV to pass through their network traffic. So they all have their own direct interface to the NIC. So it's basically like a DPDK type of scenario. They're all talking directly to the hardware, and then from that point on, you need to make the explicit assumption that the network interface, the network is managed in an isolated manner, right? Obviously, there's a whole tower of assumptions under that for information flow, right? This is why I said again, information flow is the massively more optimistic target, right? That's the really aggressive target, is full information flow. Is you really have to lock down a system a lot to get that. What I anticipate being the most useful result, and the one that we are targeting initially, is the integrity, right? I cannot overwrite your memory. You cannot directly read mine, right? You can't map mine and read it. Not a result that you can't infer anything about what I'm doing based on whether you block on an endpoint, right? That's the confidentiality side that we're not targeting to start with.
Piggybacking on to that, are you taking a similar approach with how each VM is getting a block device?
Yes. Okay. So the block devices, at least in the initial design, and all of this is somewhat subject to change based on customer feedback. But the model at the moment is that you have a block device provided to you by the VMM, and this is going out over, again, another SR-IOV mediated virtual function. So you're going out into the separate storage network.
Me again. A bit more high-level question.
Yeah.
At the start, in your motivation slide, you talked about kind of commercial cloud providers having different motivations than what you're targeting.
Yes.
So they have commercial motivations, you have other motivations. How does that translate to practice? So how do you imagine that Atoll is different than what Amazon has or other providers have?
So Amazon will not give you any formal guarantees at this level, right? We will be able to give you a proof of isolation between your VM and those of anybody else who happens to end up on the same machine as you. Amazon will try very hard to isolate you, but they'll only ever give you a best effort guarantee. So if you are, for example, and again, a lot of the pitch stuff so far has been tailored to a Swiss audience, but if you are, for example, a bank, and you have a requirement to host data locally, right? You must host it within this jurisdiction. We can give you an ironclad guarantee that your data is absolutely within this jurisdiction. And so you can just get a tick box on your certification. Whereas the process with somebody like Amazon, certainly if you're willing to pay, they'll give you something. But we would claim that we can give you a more reliable story.
There are a number of people here who care about device virtualization and the fact that seL4 does not support it dynamically, only in a very static setting. And it seems like your framework would require some kind of dynamic device virtualization. What's your state of ambitions of doing that and verifying it?
My state of ambitions right now is that I'm going to write on the BOF sessions IOMMU, right? A verified IOMMU and proper v3 IOMMU, we need it, right? Otherwise, I mean, you cannot build real systems without DMA, I'm sorry, right? This has to happen, and this is where I anticipate us being able to make a contribution.
Hello. You mentioned the Amazon case, so I'm just curious what the story behind attestation in your scenario, because if assume I have a VM, I want to verify that I'm actually running on the signed hypervisor. So what's the whole story there?
Well, so attestation would be through something like the equivalent of the TPM. That certainly exists in the platforms we're targeting. Like being able to do TPM-style attestation is, yes. You could 100% do that. Attestation is, however, only a part of the story, right? That just tells you that you are definitely running the correct, insecure, buggy version of the code, right? Including UEFI, which is the elephant in the room for anything running on a serious platform, but all the rest of the firmware, right? So like I had a plant in the audience earlier who asked about the trusted firmware, because this is a massive vector for attack. There's these mountains of stuff, which the story on these is not real good. They're sometimes written okay. UEFI is a huge big mess. That is an open question for all of us. So attestation, yeah, no trouble. Showing that your boot process was actually correct, not so easy.
Still have a little bit of time.
I think we have one. No, Jim was pointing here. Yes.
One question is how, as a VM, how do you know you're running on your Atoll software and not on something that's
That's just emulating Atoll.
Exactly.
Yeah. So this is this is Baudrillard, right? Are you living in a simulation? So talking to the TPM, you've seen the Matrix, right? Talking to the TPM is, or the equivalent of the TPM, is the only solution that anybody has presently for this, right? Because you can emulate any API, right? And there's no way to tell that. The cryptographic approach that the TPM gives you is the only convincing way to do that as it stands, right? So that you, in principle, you can simulate any interface you like, right? You can pretend to be whatever you like. But the TPM argument is, well, yes, to do that, you'd also be able to have to forge a cryptographic signature, which in principle you can do, but in practice you can't, because it's infeasible. Yeah, I mean, of course. There are always limits. There are always assumptions.